Okay, so this final example is asking us, with a given molar Gibbs energy equation or some expression for it, it asks us to obtain the equation of state for the gas. So remember, if we need to obtain an equation of state for a gas, it means we need to find an equation where we have an expression for a measurable quantity. So in other words, V, T, P, or N. Something that we can measure. These things we can actually measure in a lab. We can't measure the entropy, for example. There's no probe that we can stick into a gas and say, oh, the entropy is minus 24 joule per Kelvin, for example, per mole or whatever. Nothing that we can do like that. We need to take derivatives of slopes of graphs of calorimetric measurements that we take and whatever. But we can measure the volume, and we can measure the temperature and the pressure of whatever of a gas and whatnot. So how can we connect this Gibbs energy to one of these values? Right, so that should be something that shouts Maxwell equations, should be shouting something to you now. And in fact, if you look at the table, then there are two Maxwell equations that are options. The one is the G dt at constant pressure is equal to minus the entropy, or we can have dg dp at constant temperature, equal to the volume. So of course, we'll just quickly analyze these. This one contains entropy. We can't really measure entropy. We can't really do anything with that. This one gives us volume. So if we take the derivative of this function to pressure at a constant temperature, we will obtain the volume of this gas. So in other words, that will give us a way to determine the equation of state. So in other words, we will have something that says volume is equal to some other stuff, right? Just like PV is equal to nRT, you can write then P is equal to nRT over V, right, for a perfect gas. So for a perfect gas, you can write V is equal to nRT over V, over P. Just like you can write that, we can have now a way to write V is equal to something for this gas, right? And that's essentially where we want to end up. So if we take it, then that V is equal to dg, I'm just going to call it gm, over dp at constant temperature. So it means if we see a temperature in our equation, that becomes constant. And then we just drop that, so it just becomes ddp of that thing. It's RT ln P plus A plus BP plus a half CP squared plus a third dp cubed. Right. So if we take each of these, the derivative of this first one, so R and T, RT we established as a constant in this case because that's how we're working with. R is a constant, so we write R and T are constants. And the derivative of ln P to P means we get 1 over P, right? So we have here 1 over P. The derivative to P of just A is just a constant, becomes 0. The derivative of BP to P, it becomes just B because the derivative of P to itself just becomes 1. The next one, we're left with a half C because those are both constants. And then we're left with 2p because the derivative of p squared to p is 2p. Right. And finally, we're also left with a third d and then 3p squared. Right. Okay. So let's just write this out neatly. RT over p plus b plus this one of course becomes then just cp, and the last one just becomes dp squared. Just to remind ourselves, this is the volume. So the volume is equal to something containing p in this function. Remember, p and t, in fact, we have an equation with r, p, and t, and there's a b, a c, and a d, which are all just constants. And actually, if you recall from theme 1, that this is the Wirral equation. Can't remember how to spell that, so I'm not going to spell that. The Wirral equation of state, which is actually just a Taylor expansion, but anyway, that might fly over some people's heads. The Wirral equation of state, which we derived. Right, so very cute example, you know, for you. So essentially, if you get asked this kind of question, you just want to find an expression for either v, t, p, or n to relate whatever function you're given to either of these quantities which are measurable, and give the final function. Okay, that is essentially